3i Atlas just accelerated, and it's really dramatically. It was supposed to slow down. Every calculation said it should. But in late October 2025, the interstellar object known as 3i Atlas did the opposite. It accelerated. Not slightly, not within error margins, but dramatically. Against gravity, against every known law of orbital mechanics, and in doing so, it became the most confounding object humanity has ever observed. Tonight, we're diving into the new data, the physics, and the silence that followed inside the world's observatories. Because if these numbers hold, 3i Atlas didn't just accelerate, it may have revealed something deeper about motion, energy, and control in interstellar space. Before we begin, make sure to like and subscribe so you don't miss the next analysis as this story evolves in real time. Comment where you're watching from and what time it is there. Because as of now, the universe just got a little less predictable. This is the 3i Atlas channel, calm, focused, and based on real-time solar system data. If you want to be part of this mission, hit subscribe right now. Comment Atlas below to enter the giveaway for our exclusive 3i Atlas hoodie. Tell me where you're watching from and the exact time it is. You're now part of a global community tracking something the textbooks never prepared us for. Stay until the end, because by the time you reach the final chapter, you'll understand why this single event, silent, brief, and almost ignored, might become the most important observation of the decade. Now, let's begin. For months, every model said the same thing. 3i Atlas would approach the sun, slow as gravity pulled against it, and then drift quietly back into the void. Nothing about that prediction was controversial. Every interstellar object we've ever tracked behaved exactly that way. So when the numbers from NASA's Punch satellite arrived on October 30th, 2025, what they showed didn't just surprise analysts, it unsettled them. At 0417 UTC, the telemetry curves that describe an object's speed versus distance stopped matching their predictions. The data from the wide-field imager showed a small but unmistakable bend in the line. The object was gaining speed, not decelerating, not coasting, accelerating. The change wasn't random noise, it persisted across frames and grew stronger with every update. Within minutes, technicians at the Jet Propulsion Laboratory were recalculating orbital parameters. The deviations weren't supposed to exist, yet they did. When engineers first noticed it, they assumed a sensor fault, cosmic ray interference, perhaps a calibration glitch. But when Stereo A and GOES 19 confirmed the same trend from different vantage points, the conversation inside the control room changed. What they were seeing wasn't a mistake in math. It was a mistake in expectation. Something out there, something invisible, was applying force. Acceleration in space is sacred territory. It implies interaction. Comets accelerate when they vent gas. Spacecraft accelerate when they fire thrusters. Everything else obeys gravity alone. 3i Atlas wasn't supposed to be different. It was supposed to be inert, a frozen shard from another star system, moving through ours on a one-time trajectory. But instead of following the laws written in every textbook, it had just rewritten one. By midday, the Anomaly report reached the minor planet center. The change in velocity was small in absolute terms, fractions of a meter per second squared, but enormous in implication. Over days, it would translate into thousands of kilometers of drift from its predicted path. That's enough to make astronomers question every constant in their equations. A few veteran dynamicists quietly suggested solar radiation pressure. Others said internal gas jets. But neither model fit the timing. The acceleration began after perihelion, precisely when solar heating should have started to decline. Inside observatories across 3 continents, researchers opened the raw image stacks. They compared timestamps, filtered cosmic noise, and aligned star fields. The data lined up perfectly, no instrumentation error, no missing frames, just a persistent, measurable increase in speed. Some described the realization as the click, the instant your mind accepts that something impossible just happened. In Hawaii, the Mauna Kea Observatory tried to reacquire visual confirmation, but the object was still too close to the sun's glare. For now, only the space-based eyes could see it. The irony wasn't lost on anyone. Humanity's instruments were witnessing an event no human eye could observe directly. When the report finally went public, the wording was cautious. Non-gravitational acceleration detected, under investigation. A sterile phrase masking the magnitude of what it meant, because behind that sentence lay the possibility that the force acting on 3I Atlas wasn't random, wasn't natural, and wasn't supposed to be there. That evening, forums lit up with speculation. Scientists debated data integrity. Others whispered about propulsion. A handful of engineers, reviewing the light curves, noticed a subtle correlation between the object's brightness and its acceleration, as if its reflectivity were somehow tied to the push it received. Whatever the cause, one truth settled in. The universe had just done something it wasn't meant to do. Every law of motion we teach is a simplification, but this was defiance written in numbers. On October 30th, 2025, 3I Atlas didn't just change speed. It changed the conversation about what might be drifting between the stars. That was the moment everything changed. Every force in the universe leaves fingerprints. Gravity curves trajectories, radiation heats surfaces, and time itself smooths motion into predictable patterns. When astronomers first plotted the incoming path of 3I Atlas, those patterns were clear. The orbit was hyperbolic, an open curve that would bring it near the Sun once before flinging it back into interstellar space forever. There were no mysteries hidden in that geometry. Every object from beyond the solar system behaves the same way. It arrives, it passes, it leaves. That's the law. But from the moment 3I Atlas entered the inner solar system, something in that law began to fray. Early tracking by the Atlas Survey Telescope in Chile revealed a trajectory almost too perfect, aligned within just a few degrees of the ecliptic plane, as if it had chosen a path through the same flat disk where the planets orbit. Statistically, that's rare. Interstellar visitors approach from random angles, yet this one slid in along the solar system's traffic lane like it belonged here. Scientists called it coincidence, others called it intention. As the weeks passed, its behaviour kept diverging from expectations. Most comets wobble as jets of gas push unpredictably against their rotation. 3I Atlas stayed eerily stable. Its light curve, how bright it appeared over time, rose in smooth mathematical precision, with none of the chaotic flickers that mark spinning or venting comets. When its brightness finally surged near perihelion, the acceleration of that surge was so steep that analysts at the European Space Agency had to expand the scale on their graphs just to fit it. In orbital mechanics, objects don't get to make choices. They follow the geometry of space-time, but 3I Atlas seemed to. After perihelion, when gravity should have begun to slow it, the velocity vector curved against prediction. The spacecraft tracking network known as DSN-42 flagged the deviation. It wasn't huge, but it was deliberate-looking, like a course correction, not a drift. At first, the comparison that came to everyone's mind was obvious: Oumuamua. That was the first interstellar object ever discovered back in 2017. It too showed a small non-gravitational acceleration, unexplained by known physics. Yet 3I Atlas felt different. Where Oumuamua's motion was subtle, this was assertive. Where Oumuamua reflected faintly reddish sunlight, this one reflected blue. It was colder, smoother, more symmetrical. A traveller that shouldn't obey gravity alone, and yet wasn't obeying it at all. Some of the early simulation teams tried adding variables: asymmetric mass loss, thermal lag, momentum exchange from outgassing. None produced the stability seen in the data. The motion of 3I Atlas didn't just deviate, it resisted randomization. It held a clean vector, maintaining constant acceleration in a direction consistent with sunlight pressure, but inconsistent with natural comet rotation. That precision is what unsettled people most. The deeper they looked, the stranger the object became. Spectroscopic models predicted trace metals on its surface: iron, nickel, magnesium, but with a reflectivity higher than any dust-covered comet nucleus. It glinted like polished foil, not rock. When the punch satellites imaged its corona, the reflected light pattern formed a thin crescent, as though the object was flat or angled rather than round. By late November, the term obedience gap started circulating informally among mission analysts. It described the growing difference between what physics said the object should do and what it was actually doing. The name captured something uncomfortably human about the situation. 3I Atlas wasn't obeying. To most scientists, the word anomaly means opportunity, a chance to refine a model, but this felt different. It wasn't just that the models were wrong, it was that the object seemed aware of the rules it was breaking. A visitor from beyond the stars moving with purpose through a system built on predictability. It came from nowhere, followed none of the familiar patterns, and carried itself like a messenger of an equation we haven't learned yet. And as it receded from the sun, accelerating when it should have slowed, humanity was left with a single question echoing through observatories and late-night control rooms. What kind of visitor decides which laws to obey and which to ignore? There is a moment in every orbit when time seems to compress. For a comet, or in this case an interstellar traveller, that instant is perihelion, the closest point to the sun, when speed peaks, radiation intensifies, and every hidden property is forced into view. It is the cosmic truth serum. Whatever an object really is, perihelion reveals it. For 3I Atlas, that window opened on October 29, 2025. In those few hours, the object crossed within roughly 1.36 astronomical units of the Sun, about 200 million kilometers, somewhere between the orbits of Earth and Mars. It was not a dangerously close pass, but it was close enough for the Sun to dominate every physical variable. At that range, sunlight exerts immense energy, over a kilowatt per square meter of radiation, capable of igniting volatile ices, boiling trapped gases, and lighting up a cometary coma like a miniature nova. Except this time, the light behaved differently. 3 spacecraft had front-row seats to the event: Stereo A, SOHO, and the GOES-19 coronagraph. Each of them blocks the sun's glare to study the faint outer corona, but in doing so they also capture whatever else drifts through that field of view. When 3I Atlas entered it, all 3 instruments recorded the same unthinkable thing: an abrupt, asymmetric brightening that did not follow the smooth thermal curve predicted for any normal comet. The luminous intensity rose by a factor of nearly 200 in less than a day, corresponding to a brightness-distance relationship closer to sort of the power of -7.5 than to the typical to the power of -3 or -4 seen in solar system comets. That slope alone was enough to trigger alarm bells. A value that's steep means one of 2 things. Either the object is reacting violently to solar input, shedding mass faster than physics allows, or it is converting energy through a process we do not yet understand. For perspective, if Halley's Comet behaved this way, its nucleus would have evaporated in a matter of hours. 3I Atlas did not. It survived, intact, still accelerating away from the sun. Then came the second surprise: colour. The GOES-19 coronagraph's photometric filters showed an emission spectrum that shifted toward shorter wavelengths. The object was bluer than the solar background. No comet ever measured that way. Comets, wrapped in dust and organic carbon, usually redden under sunlight because blue light scatters out. But this one brightened into the blue, as though it were reflecting from polished metal or ionized plasma instead of frozen rock. Astronomers working with the LASCO C3 instrument ran immediate checks. Could it be an artifact, an internal reflection, a software filter error? None held up. The colour persisted across independent instruments and over several hours. The corona itself had remained stable. The only variable changing was the object. What makes perihelion such a powerful diagnostic moment is that every known natural effect, outgassing, radiation pressure, dust scattering, scales predictably with solar distance. If a body brightens faster than those laws predict, it is telling you that something else is driving it. For 3I Atlas, that something else appeared right at the moment of maximum solar stress, as though the proximity to the sun had activated a hidden function. Meanwhile, from Earth, the event was invisible. Solar conjunction buried the object in daylight. Ground telescopes were blind, and radio observatories could not risk pointing antennas that close to the sun. Humanity's only witnesses were machines orbiting far from home, relaying fragments of data through static-filled downlinks. When those fragments were reconstructed, the picture that emerged was both breathtaking and unnerving. A glowing envelope nearly 300,000 kilometers wide surrounded the nucleus, about 25 times the diameter of Earth. Within that envelope, the brightness fluctuated with an internal rhythm, pulsing faintly every 40 minutes. Some called it thermal oscillation, others energy modulation. In those few hours around perihelion, every assumption about what 3I Atlas was supposed to be collapsed. The window had opened, the sun had stripped away the pretense of normalcy, and something utterly unfamiliar had revealed itself. By the time Earth rotated back into the right alignment to see it again, the window had already closed, but the data remained, and so did the question that would define every chapter to follow. Did the sun awaken a comet, or expose something built to endure it? In science, numbers are supposed to bring comfort. They make the universe measurable, predictable, and familiar. Every orbit, every pulse of light, every faint echo from deep space can be described by them. But sometimes numbers do the opposite. Sometimes they whisper that the universe is breaking its own rules. That was the case with the data from 3i Atlas. The figures began arriving in the early hours of October 30th, 2025. Analysts at NASA's Jet Propulsion Laboratory were running routine orbit refinements when one of them noticed a slight deviation in the radial velocity. It was subtle at first, a shift so small it could have been a rounding error. But as additional data points came in from Stereo A and the Punch satellite, the trend became impossible to ignore. The object wasn't just moving, it was speeding up. By mid-morning, 3 separate datasets confirmed the same thing, an unexplained acceleration pushing 3i Atlas away from the sun. The numbers read approximately 135 km per day squared in the radial direction, with an additional 60 km per day squared transverse to its path. To most people, those units mean nothing. But to orbital engineers, they were unthinkable. Comets can experience minor thrusts from outgassing, a few millimeters per second squared perhaps. But not this. This was too consistent, too powerful, and too clean. The first reaction was disbelief. Calibration was checked. Code was recompiled. Teams reran the same sequence of images through independent pipelines. Each attempt produced the same curve. The acceleration was real. And the more precisely they measured it, the more it refused to fade into error bars. Then came the brightness data. Astronomers comparing images from GOES-19 and SOHO noticed that 3i Atlas wasn't following the usual pattern of dimming after perihelion. It was brightening explosively. When they fit a line through the photometric points, the relationship between brightness and heliocentric distance yielded an exponent of -7.5. In plain terms, for every small step the object took away from the sun, it grew hundreds of times brighter. No comet had ever done that. Typical slopes range from -3 to -5. Anything beyond -6 defies accepted thermal physics. If the numbers were correct, the object's luminous intensity increased faster than the square of its received sunlight. That means the energy it radiated was not merely reflected, it was being generated. A comet can't do that. A rock can't do that. Inside the European Space Operations Centre, the mood turned from curiosity to unease. The more data they processed, the further the models drifted. Standard comet equations broke instantly. Substitution tests using sublimation rates of water ice, carbon monoxide, or even exotic compounds all failed to produce the observed acceleration. The only way to reproduce the numbers mathematically was to assume that the object was almost weightless relative to its surface area, something thin, reflective, and massive in size. That suggestion circulated quietly in emails and encrypted chats. Someone compared it to a solar sail, another to the relic of a derelict probe. Officially, those theories were dismissed as speculation. Unofficially, they explained the data better than any natural model on record. As the reports compiled, the phrase non-gravitational anomaly began appearing in every draft. It is a neutral term, safe for publication, but everyone involved knew what it really meant. The data had forced them to write a sentence they never expected to write. Gravity alone cannot describe the motion of this object. The final check came from the team at the Minor Planet Center. Using observations collected over 5 weeks, they compared predicted versus measured positions. The residuals were no longer random noise. They curved in one consistent direction, outward, away from the sun. When plotted, the deviation formed a graceful, impossible arc. Numbers usually end debates. This time, they started one. They told a story that mathematics could describe but not explain. A story about a traveller from another star accelerating as if guided by something unseen. Every instrument agreed, every variable aligned, and every scientist who looked at the graphs came to the same quiet conclusion. Something out there had just rewritten the equation. Every act of motion demands an exchange. A rocket accelerates because it throws exhaust in the opposite direction. A comet speeds up when jets of vapor erupt from its surface. Even sunlight can push, but only if something wide, light and reflective catches its photons. Nature does not give free acceleration. Yet, in the days after perihelion, 3i Atlas moved as if that rule no longer applied. The first suspicion was propulsion by sublimation, the same process that powers comets. When frozen gases trapped under the surface heat up, they escape through vents, creating thrust. But 3i Atlas was already beyond the distance where such activity normally fades. Infrared spectra from the James Webb Space Telescope detected little to no water vapor. Carbon dioxide levels were far too low to generate the observed acceleration. The object was not venting, it was gliding, perfectly, silently, yet it was still gaining speed. At the Jet Propulsion Laboratory, engineers ran energy balance models to estimate what kind of mass loss would be needed to produce the recorded acceleration. The answer made no sense. For 3i Atlas to reach those velocities using sublimation, it would need to eject thousands of tons of material every hour. That much activity would surround the object with a visible coma and a long dust plume. No such structure appeared. The region around it remained clean, thin, and sharply defined. If not gas jets, then what? Solar radiation pressure was the next logical candidate. Light itself exerts force, but the effect is minuscule, barely measurable except on extremely low-mass objects. A perfect mirror 1 kilometer across could be pushed by sunlight at a rate that roughly matches the numbers seen in the telemetry. The problem is that 3i Atlas is not a kilometer-wide mirror. It was estimated to be between a few hundred meters and a few kilometers in diameter, with a density typical of icy rock. Radiation pressure could not move something that heavy so efficiently, unless, of course, it was not heavy at all. That single possibility changed the tone of the internal discussions. If the density of 3i Atlas was far lower than expected, if it was thin, hollow, or built from materials engineered for reflectivity, then the puzzle made sense. The object could be accelerating under the faint but constant pressure of sunlight. A structure designed for that purpose would need no engine, no exhaust, no fuel. The sun would be its motor. In Cambridge, Avi Loeb's research group modelled the object as a light sail, a sheet of reflective material only a few millimeters thick, with a mass-to-area ratio optimized for photon propulsion. The resulting acceleration matched the measured values almost exactly. The simulation was elegant, almost too elegant. Critics called it premature. But no one could find a simpler explanation that fit the data. The phrase non-gravitational acceleration began appearing in every technical bulletin. It was a careful way to say what everyone was thinking. There was a force acting on the object, but no visible source for that force. No thrust plumes, no mass loss, no internal heat spikes, a push without a pusher. The absence of evidence is not proof of the extraordinary, but in physics, sustained acceleration with no exhaust is as close to heresy as it gets. Objects do not move themselves. Yet every sensor from Stereo A to GOES 19 agreed. The acceleration vector was smooth, consistent, and solar aligned. Whatever was pushing 3i Atlas did not flicker or fade. It was steady, as if tuned to the rhythm of sunlight itself. By mid-November, the situation had crossed from anomaly to mystery. The equations balanced only when something unorthodox was added to them. A reflective surface, an unknown interaction, perhaps even a property of matter not yet measured in our laboratories. Observatories continued to track it, hoping for turbulence, a sign of fragmentation, anything to restore the comfort of chaos. None came. A force was present, measurable and precise, yet no engine could be found. And somewhere beyond Mars's orbit, 3i Atlas kept climbing, obeying a propulsion system that physics had not yet named. Color is the language of energy. It reveals temperature, composition, and the hidden physics behind what our eyes cannot see. Every star, every gas cloud, every comet speaks in this spectrum. Reds tell of warmth and dust. Yellows mean sunlight scattered through neutral material. But blue, deep, electric, unnatural blue, almost never comes from a comet. That is why the readings from 3i Atlas sent such a chill through the astronomy community. The first sign came from the GOES 19 coronagraph, a satellite designed to watch solar storms, not interstellar visitors. Its instruments split light into separate wavelength bands to measure how the sun's outer layers glow during flares. When 3i Atlas passed through its field of view, the detectors registered a spectral slope that leaned sharply toward the short end of the spectrum, the blue side. The signature was real, not a processing artifact. It held steady for hours, even as the object moved through different filters. To understand how strange that is, consider what normally happens when sunlight strikes a comet. Dust grains, carbon molecules, and organic residues absorb blue light and reflect red, giving most comets their familiar yellowish hue. Only a few ever show hints of green or cyan, usually from molecules like diatomic carbon or cyanogen glowing under ultraviolet radiation. None glow bluer than the sun itself. That is physically extreme. It means the object's visible light output peaks at shorter wavelengths than the source illuminating it. Spectrophotometry teams at Stereo A and SOHO ran independent calibrations to confirm. They compared 3i Atlas's brightness ratios in red and blue channels against the solar reference spectrum. The result was consistent. The color index was negative. In plain terms, it was bluer than the star it was orbiting. At first, the explanation seemed simple: Rayleigh scattering. When light passes through a cloud of very small dust particles, shorter wavelengths scatter more efficiently, just as Earth's sky turns blue. But that effect requires particle sizes smaller than half the wavelength of light, on the order of nanometers. The coma around 3i Atlas was vast, extending hundreds of thousands of kilometers, and too dense for such uniform grains. The brightness was also too high. The math ruled it out. Next came the plasma hypothesis. Perhaps high-energy electrons from the solar wind were exciting atoms in the object's coma, producing emission lines near the blue region of the spectrum. That could happen in theory, but the intensity was again too strong and too broad. Emission from ionized oxygen or hydrogen would create narrow spectral peaks. What GOES 19 saw was continuous, a wide, even glow stretching across the visible band. It looked like reflection, not emission. Then a more controversial idea began circulating. The blue might come from the surface itself. A reflective layer, smooth at the microscopic level, could scatter short wavelengths preferentially if its composition favoured metallic bonding or dielectric interference, properties typical of engineered materials, not natural ices. Laboratory comparisons with aluminum, magnesium oxide, and thin film silicates produced similar spectral slopes. The more the data was modelled, the more it resembled a mirror. Researchers at the European Space Agency's Optics Division simulated possible surface coatings, a mixture of magnesium silicate crystals and carbon, nanostructures layered in microscopic films, could in theory reproduce the observed blue shift. But such layering requires formation conditions far beyond comet chemistry: intense heat, controlled pressure, and precise molecular alignment. Processes, in other words, that occur in factories, not in deep space. The debate intensified after the James Webb Space Telescope analysed the object in the near-infrared spectrum. Instead of the expected thermal peak for an object so close to the Sun, Webb detected a relative dip. It was colder than its brightness suggested. A material that reflects strongly in visible wavelengths while absorbing little heat would behave exactly that way. The reflectivity would cause apparent luminosity without raising temperature. At conferences, scientists avoided using the word artificial. They preferred non-standard scattering mechanism. But everyone understood the implication. 3i Atlas was not just reflecting sunlight, it was manipulating it. Something in its outer shell was tuned to short wavelengths, amplifying the blue end of the spectrum like a signal, clean and deliberate. Colour is information, and in this case it carried a message that physics could not easily translate. The sun had illuminated a visitor from the dark, and the light that came back was not random. It was blue, a colour too pure, too symmetrical, and too persistent to be accidental. In a universe where most things burn red, 3i Atlas glowed the colour of mystery. When something in the sky behaves strangely, the first instinct of every scientist is to compare. Comparison anchors the unknown to what we already understand. It is how astronomy turns chaos into data, by finding a familiar pattern hiding behind a new signal. So when 3i Atlas began defying the models, the search for analogues began immediately. The first candidates were obvious: Oumuamua and Borisov, the only two confirmed interstellar objects before Atlas. Both had rewritten small chapters of celestial mechanics, but in different ways. Oumuamua had arrived in 2017, elongated, tumbling and accelerating slightly as it left the inner solar system, though no coma was visible. Borisov followed in 2019, unmistakably cometary, venting gases and behaving exactly as physics predicted. If Oumuamua was the enigma, Borisov was the reassurance. Between the two, astronomers thought they had framed the limits of interstellar visitors. Then came Atlas, and the frame shattered. Like Borisov, Atlas produced measurable light long before perihelion, implying active outgassing. But the rate of brightening was far too steep. Like Oumuamua, it showed non-gravitational acceleration, yet its path was smoother, steadier, and far more powerful. It did not tumble, it did not flicker. Instead, it glided through the inner system as if stabilized, an object maintaining attitude control without any visible jets. When analysts tried to fit it onto the same models that explained its predecessors, the residuals exploded off the charts. One by one, every known comet family was tested. The Halley-type comets, with their high inclinations and volatile ices, could not explain the sustained luminosity. Jupiter family comets, small and dusty, lacked the energy to produce the observed blue shift. Even long-period Oort cloud visitors, the most volatile of all, failed to replicate the brightness curve. Every line on the graph bent too shallow. Every simulation demanded mass loss and fragmentation that never appeared in the data. A team at the European Southern Observatory ran compositional models using common ice ratios: water, carbon monoxide, carbon dioxide, ammonia. None fit. The observed acceleration required mass loss equivalent to ejecting an entire mountain of ice every day. But the thermal infrared readings showed no increase in temperature, no expanding coma, no surrounding dust cloud. 3I Atlas was accelerating cleanly, like a craft, not a crumbling snowball. Another comparison was geometric. Most natural bodies rotate irregularly, scattering light unevenly and producing oscillations in brightness. But the light curve of 3I Atlas was eerily smooth, with barely perceptible modulation. The rotation period, if one existed, had to be either incredibly slow or perfectly aligned with the observer, a coincidence too exact for comfort. By November, the comparisons had grown desperate. Researchers reached deeper into the archives, to disintegrating comets, to asteroid impacts, even to the small outburst of Comet 17P Holmes in 2007, when its brightness briefly surged by 1,000,000-fold. Yet even that spectacular explosion left traces of debris and thermal excess. Atlas left none. It grew brighter and faster, then steadied into silence. At a closed meeting between NASA and the European Space Agency, one slide summed up the crisis. No natural analogues within observational record. It was as close to an admission of failure as scientific language allows. Every hypothesis that depended on familiar physics had collapsed under its own weight. What remained were the outliers, hypotheses that pushed against the edge of possibility. Some proposed exotic chemistry, ices made of unfamiliar molecules from another stellar nursery, perhaps hypervolatile compounds that could ignite in patterns unseen before. Others suggested electrostatic propulsion, driven by solar wind charge differentials, and in the corners of the discussion, more daring voices whispered what others avoided saying aloud. The shape, reflectivity and acceleration matched the theoretical behavior of a thin light sail. Still, the official papers stayed cautious. They spoke of data incongruence, anomalous consistency, and comparative model failure. But behind that language was a quiet acknowledgement that the comparisons were over. 3I Atlas belonged to no known class of object. In the end, the catalogue of analogues did more than fail. It revealed the limits of our imagination. Every model we trusted bent around the anomaly like light around a black hole, warped but intact, unwilling to break. And in that resistance, something profound became clear. We might be witnessing a kind of object our solar system has never produced, shaped by forces that our physics only begins to describe. For decades, comparisons have guided discovery, but this time, comparison became confession, a way of admitting that nothing in the sky behaves quite like this visitor. And until we find another, 3I Atlas stands alone. The discovery should have been followed by excitement. Interviews, press conferences, and celebratory papers. That is the rhythm of science when the universe surprises us. But when 3I Atlas began accelerating after perihelion, excitement was replaced by something else. Silence. It began quietly, as most silences do. Data teams at NASA's Jet Propulsion Laboratory, the European Space Agency, and the Minor Planet Center exchanged emails late into the night after the first reports of non-gravitational acceleration appeared. Normally, such a finding would have sparked an immediate public release. This time, no statement came. The analysts were told to verify, re-verify, and wait. The reason was simple. If the data were wrong, the world would mock them. If the data were right, no one knew how to explain them. Inside observatories across 3 continents, people stopped talking publicly about Atlas. On internal networks, the graphs circulated, velocity curves that bent upward instead of flattening, brightness indices that defied the models. Every chart told the same story, but no one wanted to attach their name to it yet. When a young researcher at the European Southern Observatory posted a preliminary plot online, it vanished within an hour, quietly deleted, replaced by an older version with the anomaly cropped out. By early November, mission leads at Punch and Stereo had received identical memos marked restricted distribution. They were instructed to limit further commentary until a cross-agency review confirmed the results. No one called it a gag order, but that was what it felt like. Some within the scientific community defended the restraint, calling it professionalism, the responsible act of verifying before alarming. Others called it fear. The silence extended beyond institutions. Independent astronomers noticed the gap in updates. Normally, the Minor Planet Center posts refined orbital parameters daily. For Atlas, days went by with nothing. Amateur observers on astronomy forums began speculating that the data had been pulled. They were partly right. The latest orbital solution, showing a measurable outward drift, had been flagged for internal revision and never re-uploaded. Inside the silence, collaboration gave way to tension. Some scientists wanted transparency, arguing that the public deserved to know even if the anomaly later proved mundane. Others worried about credibility. The memory of Oumuamua's controversy was still fresh, how a single mention of artificial origin had turned cautious research into tabloid spectacle. No one wanted a repeat of that. So the silence thickened. Meanwhile, the object kept moving. Day by day, the acceleration persisted, constant and elegant. Spacecraft telemetry recorded the drift in real time, but those numbers stayed inside encrypted folders, accessible only to a few. Teams tasked with drafting the public summary began editing each other's language until it read like every other routine update. Words like anomalous, unexpected, and non-physical were replaced with neutral phrases, pending confirmation, subject to calibration. In December, a meeting was held at the Harvard-Smithsonian Center for Astrophysics. Representatives from NASA, ESA, and several national observatories joined over secure video channels. According to one attendee's notes, the discussion focused less on science and more on timing, when to publish, how to phrase uncertainty, and how to keep the speculation manageable. The consensus was to say nothing until the object re-entered Earth's line of sight later in the month. Outside that circle, the silence grew louder. Journalists noticed the absence of updates. Online, rumours began to multiply. Talk of a hidden craft, a government cover-up, a second Oumuamua. But beneath the noise, the professionals stayed quiet. Not because they knew too much, but because they knew too little. The data was solid, but the implications were not. For scientists trained to trust observation, that is the hardest silence of all. It is not the silence of secrecy, but of uncertainty, the heavy pause between discovery and understanding. In that pause, reputations hang, careers tremble, and humanity waits for words that do not yet exist. And so, for weeks, the greatest anomaly in modern astronomy remained unspoken. The object that should have been shouted from every headline drifted deeper into the dark, carrying with it a truth too fragile to declare. 3. Atlas had done something no interstellar visitor should ever do, and in response the world's brightest minds said nothing at all. By the time the data was undeniable, the silence had reached its breaking point. Someone had to propose an explanation. The community needed a framework, however tentative, to stop the growing unease that surrounded 3i Atlas. That is how, in early November 2025, the first official shortlist of theories was drafted, not in a press release, but in a shared digital document circulated between NASA, ESA, and several university astrophysics departments. It was titled simply Non-Gravitational Acceleration Mechanisms for 3i Atlas. Inside that document were three possibilities, just three, and each, in its own way, failed to satisfy the data. The first was the natural outgassing model, the same mechanism responsible for the gentle thrusts that alter the orbits of ordinary comets. As volatile ices vaporize under sunlight, jets of gas and dust act like small thrusters, nudging the body off course. This model was safe, conventional, and entirely inadequate. Spectroscopic data from the James Webb Space Telescope and SOHO showed only faint traces of carbon dioxide and carbon monoxide, and water vapour was nearly absent. There was no coma dense enough, no plume powerful enough to account for the acceleration recorded by punch and stereo. Even if hidden jets existed, their geometry would have caused irregular fluctuations in the trajectory. The object's path was smooth, unnaturally so. The second theory turned toward radiation pressure, the push of sunlight itself. Light carries momentum. When photons strike a reflective surface, they impart a tiny force. Under normal conditions, that force is negligible, far too weak to move something the size of 3i Atlas. But if the object were extremely thin and light, the math changed. Engineers calculated that a reflective surface with a mass-to-area ratio below 1 gram per square meter could experience exactly the observed acceleration at 1.36 astronomical units from the Sun. The numbers matched perfectly. The question was whether nature could create such a structure on its own. To test that, materials scientists ran simulations of ice fracturing in vacuum conditions, imagining a comet nucleus splitting into thin sheets of frozen carbon dioxide or silicate dust. The results were discouraging. Such sheets would disintegrate within hours, torn apart by micrometeoroids or radiation. No natural process could create a stable sail, unless, and this was where the document grew bold, the sail had been built. The third theory was the internal energy hypothesis. Perhaps the object wasn't being pushed from the outside at all, but from within. A chemical or thermal process beneath its surface could release energy gradually, driving motion without visible exhaust. It was an elegant thought, a self-contained system venting from hidden cavities, invisible to telescopes. But physics crushed the idea quickly. The energy required to sustain such thrust for weeks would generate detectable heat, yet infrared readings from the James Webb Space Telescope showed the opposite. 3i Atlas was cooler than expected, not hotter. It was absorbing less sunlight than a rock of similar size should. That meant either it was reflecting almost all incoming radiation, or it was actively managing its temperature, and that was where the shortlist ended. 3 ideas, none sufficient. At the bottom of the document, one unnumbered line appeared. Additional mechanisms under consideration. Photon-enhanced propulsion, magnetic interaction, artificial origin, not for publication. That parenthetical note said more than all the data combined. It acknowledged that science had reached the edge of what could be explained without reimagining what kind of object this was. In the following days, the shortlist circulated quietly between research institutions. Some edited it, others ignored it. A few deleted the last line before forwarding it onward, but those who read the unedited version understood what it implied. 3i Atlas wasn't just a comet acting strangely. It might represent a category we had no name for, a structure that obeyed physics precisely, but followed no natural process to exist. 3 theories, 3 failures. The shortlist had been meant to simplify the chaos. Instead, it became a mirror reflecting how little we truly understood. Every comet tells its story through vapour. When sunlight warms an icy nucleus, frozen gases burst free, venting into space and forming a luminous coma that drags dust into a sweeping arc. That reaction is predictable. It explains why comets brighten as they approach the sun, why they veer slightly off course, and why their trajectories can be modelled down to fractions of a second. Outgassing is the heartbeat of cometary physics, the small invisible engine behind their motion. So when 3i Atlas began accelerating after perihelion, The natural assumption was that it was simply outgassing more than expected. There was comfort in that explanation. It was familiar, mechanical, and measurable. But almost immediately the data began to dismantle it. The first red flag came from infrared spectroscopy. Instruments aboard the James Webb Space Telescope and SOHO's SWAN detector searched for the distinct emission lines of water, carbon dioxide, and carbon monoxide, the molecular fingerprints of a comet under heat. They found only traces, faint and inconsistent. Water, the usual driver of post-perihelion activity, was almost absent. Carbon dioxide levels were too low by an order of magnitude to explain the measured acceleration, and methane, a possible alternative, was missing entirely. Then came the visual evidence. The coronagraphs of Stereo A and GOES 19 captured the object in clear sunlight. No plume, no jets, no haze. Where a normal comet would show a fuzzy halo of gas and dust, 3i Atlas remained sharply defined, a pinpoint of blinding light surrounded by empty space. Even with extreme image processing, astronomers could not find a single jet or dust trail. The nucleus was clean, polished, almost surgical. If there was no visible outgassing, how could there be thrust? Astrophysicists turned to mathematical modelling. If sublimation were somehow occurring beneath the surface, pressure could build up in sealed pockets, forcing microjets through narrow vents too small to be resolved by telescopes. These invisible leaks might act like thrusters, producing steady acceleration without the spectacle of a traditional tail. It was an elegant compromise, one that satisfied both skeptics and believers. But the numbers did not cooperate. For those hypothetical microjets to sustain a radial acceleration of 135 kilometers per day, squared, the total mass ejected would need to exceed 10,000 kilograms per second. That much outflow would erode kilometers of surface material each week and flood the region with detectable vapor. Yet spectra showed none. The energy budget didn't balance. Next came the thermal paradox. As a comet outgasses, its surface cools. Vaporization absorbs heat. But readings from the James Webb Space Telescope indicated the opposite. 3i Atlas's surface temperature remained steady, not dropping. In fact, it appeared cooler than expected, as though it were resisting heat entirely. A comet that does not warm cannot outgas. Some researchers suggested exotic chemistry, ices of ammonia or cyanogen that might sublimate at lower thresholds and leave weaker spectral fingerprints. Others invoked electrostatic effects, solar-wind interactions that could mimic thrust. But every alternative carried the same flaw. Each required some trace evidence of gas or plasma. None appeared. By mid-November, the phrase outgassing paradox began circulating internally. It captured the contradiction perfectly. A force consistent with jet propulsion, but lacking any of the material signs. The paradox wasn't just mathematical, it was philosophical. It implied that the object was performing the action of outgassing without the process itself, like a voice with no breath behind it. At a closed workshop in Geneva, comet dynamicists revisited the fundamentals. Was it possible, they asked, that 3i Atlas had no volatile surface at all? That its structure was something solid, reflective, and engineered to respond to sunlight in a way that mimicked propulsion? The suggestion was quietly removed from the meeting minutes, but the conversation lingered in every mind that heard it. Because if 3i Atlas wasn't outgassing, then what was it doing? If there was no vapor, no thrust, and no heat, the only remaining explanation was unsettling, that the object was accelerating through a mechanism that looked like sublimation, but operated on a principle far more deliberate. And so, the outgassing paradox became more than a technical mystery. It became a symbol of the limits of our instruments, our models, and perhaps our imagination, a silent reminder that the universe can still perform the impossible without ever showing how. By the middle of November 2025, the conversations inside the astrophysics community had shifted from cautious curiosity to quiet disbelief. Every natural model had failed. The equations that once described comets with clockwork precision now bent under an invisible pressure. Somewhere between the data sheets and the silence, a new phrase emerged, whispered first in private chat threads, then in late-night conference calls, the light sail hypothesis. The idea was simple, elegant, and unsettling. What if 3i Atlas was not being pushed by gas or gravity at all, but by light itself? Radiation pressure, The push of photons is one of the faintest forces in nature. Each particle of light carries momentum, and when it strikes a reflective surface, it transfers a minuscule impulse. Normally, this effect is negligible. It can't move rocks or asteroids or comets. But if a structure were thin enough and broad enough, something with a mass-to-area ratio smaller than a sheet of paper, sunlight alone could accelerate it across space. The math, when applied to 3I Atlas, worked disturbingly well. At 136 astronomical units from the Sun, the radiation pressure is roughly 1,000th the strength of Earth's gravity. For an object weighing less than 1 gram per square metre, that gentle pressure could produce a constant acceleration of about 1/10 of a millimetre per second squared, exactly what the Punch and Stereo satellites had measured. No gas required, no engines, just light. To test the hypothesis, a research team at Harvard's Institute for Theory and Computation modelled 3I Atlas as a light sail, a flat or slightly curved sheet designed to reflect photons efficiently. The simulated trajectory matched the real one within 1%. The brightness curve fit too, since a sail oriented toward the sun would reflect more light as it adjusted its angle, appearing to pulse with each correction. The precision was eerie. The acceleration profile looked engineered. Skeptics pointed out that radiation pressure acts on every object in space. Why call it a sail when it could just be a fluke, a shard of debris from a shattered comet, a fragment of reflective material born from natural fracture? But that argument broke down under one observation: stability. Natural fragments tumble, they spin, wobble, and scatter light irregularly. 3I Atlas did none of that. Its luminosity curve remained nearly flat for days, suggesting that whatever surface it had, it was holding orientation, something only active control or an exceptionally balanced geometry could achieve. Others raised a simpler objection. No natural process could create a sheet of such extreme thinness. Ice crystals sublimate, dust disperses, even the most delicate cometary films tear apart in sunlight. For the light sail model to hold, the material would need to be both incredibly reflective and almost massless, a combination familiar to engineers but not to geologists. That comparison drew the inevitable parallel to Oumuamua. In 2017, the same Avi Loeb, who now led the 3I Atlas analysis, had proposed that Oumuamua might be a light sail, a relic of interstellar technology drifting through our system. Back then, the claim was ridiculed. But with Atlas, the numbers were harder to dismiss. This time, there were no calibration errors, no missing data. The acceleration was consistent, measurable, and persistent. Within the agencies, opinions fractured. Some argued that calling it a sail was premature, that such language would ignite media hysteria. Others countered that the math spoke for itself. If it looks like radiation pressure, one researcher wrote in an internal memo, and walks like radiation pressure, then something is catching the light. Still, no one dared to speak the next sentence aloud, that if Atlas was a sail, then someone somewhere had built it. In public, NASA's official stance remained conservative. The object exhibits a non-gravitational acceleration consistent with radiation pressure. It was a safe phrase, technically accurate, emotionally hollow. Behind the scenes, though, the tone was changing. Physicists were no longer asking whether the light sail hypothesis was plausible. They were asking whose sail it might be. A thin, silent structure riding sunlight through the inner solar system, neither rock nor ice, neither debris nor probe. A visitor powered by the same star that revealed it. And as 3I Atlas drifted farther from the sun, still gleaming electric blue, one truth settled over every observatory on Earth. The oldest force in the universe might be carrying something new. Every mystery in astrophysics eventually runs into the same wall: energy. No matter how strange an object behaves, the math must still balance. The energy that goes in must equal the energy that comes out. It is the foundation of all physics, a universal accounting system that cannot be cheated. And yet, in late November 2025, 3I Atlas seemed to be doing exactly that. At first, the numbers appeared harmless. The object's brightness was increasing faster than expected, but that could have been a reflection issue, a change in angle or surface albedo. Then analysts began to calculate the energy flow more carefully. The data from GOES-19 SO-HO and the James Webb Space Telescope told a story that simply didn't add up. At its distance from the Sun, the total solar energy striking 3I Atlas should have been around 1 kilowatt per square meter. Only a fraction of that could be reflected or converted into motion. The rest would be absorbed as heat and re-radiated as infrared energy, like sunlight warming a stone. But the infrared output didn't match the input. It was far too low, by nearly 40%. The object was cooler than the surrounding models predicted, even though it was absorbing immense amounts of radiation. That discrepancy meant one of two things. Either the surface of 3I Atlas was reflecting almost all sunlight with perfect efficiency, something no natural surface could do, or the object was using the absorbed energy for something other than heat. Neither explanation fit comfortably within the boundaries of comet physics. When engineers at the Jet Propulsion Laboratory attempted to balance the energy budget, they arrived at a paradox. The acceleration required to push the object along its measured trajectory demanded an input of roughly 13 joules over the course of its near-solar passage. That energy had to come from somewhere. Outgassing could in theory supply thrust, but the observed lack of vapor ruled that out. Radiation pressure could provide it, but only if the surface reflectivity approached 100%. That would make the object more mirror-like than anything nature has ever produced. Astronomers turned to thermal modelling for answers. They calculated how quickly an icy body of a given size should heat up near perihelion. The expected result was a spike in infrared emission, a thermal flare that should have lasted several hours. Instead, the flare never came. The Atlas stayed cold, almost eerily so, as if insulated from sunlight. The thermal inertia, the ability to resist heating, was 10 times higher than that of known cometary materials. One speculative model suggested a layered structure, a thin reflective shell atop a denser core acting like a heat shield. Light would bounce off the top layer while the core remained thermally dormant. Another proposal went further, describing a self-regulating system, a surface designed to convert absorbed energy directly into motion through photon redirection or magnetic coupling. These were not theories for comets, they were theories for technology. The debate grew tense. At the European Space Operations Centre, several analysts refused to include the energy budget in their public report, fearing that it would invite interpretation beyond scientific scope. In private, though, emails circulated with blunt language. The object appears to use energy more efficiently than reflection allows. A few researchers invoked quantum-scale effects, photon tunneling, metamaterial interference, or even energy redistribution through microscopic lattice structures. It was a desperate attempt to rescue the laws of thermodynamics without conceding the unthinkable, that the energy wasn't missing at all, but being used. By December, the consensus was grim. No matter how they adjusted the parameters, composition, mass, reflectivity, the total energy leaving 3I Atlas was less than what it received. Somewhere between sunlight and motion, power was vanishing. In physics, missing energy is more than a math problem. It is a message. It tells you there's a process you don't yet understand, a mechanism operating in the dark, siphoning from the familiar into the unknown. For 3I Atlas, that message was clear. The universe's accounting system had found an entry it couldn't balance. The books no longer matched, and for the first time, the cosmos itself looked like it was hiding its receipts. Light carries secrets in the way it vibrates. When it bounces off a surface, scatters through dust, or passes through a magnetic field, its orientation, its polarization, changes. For astronomers, polarization is one of the most precise tools for decoding composition. A comet's reflected light tells you what it's made of, how its dust is shaped, and even how rough its surface is. No matter how far away the object, the polarization curve never lies. That is why, when 3I Atlas crossed the inner solar system in late 2025, polarization measurements became the next frontier of investigation. Researchers expected a familiar signature, the same gentle negative polarization seen in every dusty comet before it. Instead, what they found was something that seemed to come from another category of matter altogether. The first measurements came from the Hubble Space Telescope, using its advanced camera for surveys. The data was clean and consistent. At small phase angles, when the object was nearly in line with the Sun and Earth, its light showed a strong negative polarization that flipped direction as the viewing geometry changed. This flip was far sharper and more pronounced than in any known comet. Ordinary dust particles scatter light randomly, creating a smooth curve. 3i Atlas produced a jagged, abrupt transition, as though the light were bouncing off a flat, mirror-like surface. Teams from ESO's Very Large Telescope and the Subaru Observatory soon confirmed it. The polarization degree reached values as high as -5%, before switching positive at larger angles, a profile no natural comet has ever displayed. It was as if the surface itself was engineered to reflect sunlight differently depending on orientation. The anomaly deepened when the data was compared with the object's color index. Normally, polarization and color move in tandem. Redder light means more dust, stronger scattering, and higher polarization. But 3i Atlas broke that rule completely. Its blue spectrum coincided with an inverted polarization curve, the exact opposite of every known physical model. The implication was staggering. To produce such a signature, the surface must have been microscopically smooth and highly reflective, not rough and dusty like a comet nucleus. Physicists began exploring exotic materials that could replicate the readings: metallic powders, dielectric films, crystalline silicates fused into coherent sheets. None matched perfectly. Some suggested a composite layer, alternating bands of reflective and absorptive material arranged in nanoscopic lattices. That kind of structure can manipulate light polarization deliberately, turning it like a key. In laboratories on Earth, we call such substances metamaterials. They do not occur in nature. The Canadian Polarimetry Network, usually concerned with studying icy moons and planetary atmospheres, reprocessed the Atlas data independently. Their findings were even more precise. The angle of polarization rotated by more than 100 degrees across a viewing span of just 15 degrees. That kind of rotation demands a controlled geometry, like the layered surfaces used in solar sails or antenna reflectors. One internal report described it bluntly: behavior consistent with anisotropic manufactured surfaces. Within weeks, the term polarization anomaly entered circulation among the research teams. Publicly, the phenomenon was described as an unexpected scattering regime. Privately, it was viewed as evidence that 3i Atlas's surface interacted with light intentionally, not passively. The most remarkable moment came when the object passed beyond 1.5 astronomical units. Even as it receded from the Sun, its polarization curve remained stable, not fading or diffusing as natural comets do. That meant the surface wasn't changing, sublimating, or losing material. It was durable, intact, and possibly metallic. The final confirmation arrived from the Nordic Optical Telescope in early December. Using high-precision polarimetry, astronomers detected a faint periodic modulation in the polarization angle, a rhythmic oscillation every 40 minutes. It mirrored the same pulse period seen in its brightness data. The two signals aligned perfectly, suggesting that the object's surface orientation, and therefore its reflective geometry, was changing in a controlled, repeating way. In science, consistency is everything. Random chaos points to nature, rhythmic precision points to design. And so, as 3i Atlas drifted farther from the Sun, still shimmering electric blue, its polarization told the story the spectra could not. It was not just reflecting light, it was managing it, rotating photons, bending them, controlling their angle as though following instructions written into its surface. The universe had whispered through vibration, and for the first time, light itself seemed to be answering back. By the first week of December 2025, the discussion inside every observatory had shifted from what was pushing 3i Atlas to how. Whatever mechanism was at work, it was steady, continuous, and deliberate. It did not fade with distance, did not pulse erratically, and did not depend on outgassing or sunlight alone. It was as though something inside the object, unseen and perfectly balanced, was generating thrust from within. The idea of a hidden power source began quietly. In a meeting at the Jet Propulsion Laboratory, one researcher asked the question that everyone had been avoiding. What if it's not being pushed? What if it's propelling itself? The room fell silent. No one wanted to put their name to that sentence. But the question lingered, because the math demanded it. The constant acceleration of 3i Atlas was too smooth to be random. Cometary jets fluctuate with solar heating. Radiation pressure shifts as orientation changes. This force did neither. Over thousands of kilometers, the acceleration stayed uniform to within measurable precision. Nature rarely maintains that kind of perfection without help. To test the idea, engineers at the European Space Operations Centre built a dynamic simulation. They introduced a hypothetical internal energy source, a low consistent thrust equivalent to the power of a running lawnmower, applied continuously over several weeks. The trajectory that emerged matched the observed path with uncanny accuracy. The numbers worked. The physics did not. If an internal engine existed, it left no heat signature. The James Webb Space Telescope measured surface temperatures as cold and steady, around 200 Kelvin, far too low for any active combustion, nuclear or chemical process. No infrared plume, no trace of ionized exhaust, no magnetic interference. The energy was there, but it hid perfectly. The next theory was exotic. Perhaps the object was converting sunlight into motion in a way beyond standard radiation pressure. A process called photon momentum amplification, theoretical at best, could allow an advanced surface to trap and redirect photons internally, multiplying their push without consuming energy. In essence, it would be a self-sustaining engine of light. The equations predicted exactly the kind of thrust Atlas displayed. Skeptics argued that such a mechanism required precision nanostructures, engineered layers capable of manipulating electromagnetic fields, technology centuries beyond human reach. But when the polarization data from Hubble arrived, showing signs of anisotropic reflection and rhythmic oscillation, that skepticism began to fade. Those same properties could serve as the control system for such an engine. The correlation was impossible to ignore. In Tokyo, a team at the Institute of Space and Astronautical Science ran energy balance models assuming Atlas was absorbing sunlight selectively, converting part of it into directed momentum through unknown photonic coupling. The calculations revealed something extraordinary. Even if just 0.1% of the absorbed solar energy was converted into thrust, it would account for the entire observed acceleration. It was the smallest, most efficient propulsion system imaginable. A hidden power source that left no waste, no sound, and no trace. By now, the phrase hidden power source had become a quiet shorthand among analysts, a way of acknowledging the unexplainable without crossing into speculation. In public reports, it appeared as sustained non-gravitational energy influence. But internally, scientists had begun comparing it to ion propulsion, photon recycling, and even electrodynamic tethers, concepts that existed only in prototype spacecraft. Some dared to ask if 3i Atlas was an ancient relic, a probe powered by mechanisms that had long outlasted their creators. Others suggested it could be a naturally evolved phenomenon, an interstellar crystal harnessing the sun's radiation through resonance. Both ideas bordered on science fiction, yet both fit the data better than any classical model. What made the mystery deeper was the timing. As 3i Atlas moved farther from the sun, its acceleration should have weakened sharply. Radiation pressure and thermal activity fall off with distance squared. But telemetry from stereo and punch showed no such drop. The thrust remained constant, as if the object carried its own internal supply of energy, independent of sunlight. The more the data stabilized, the clearer it became. 3i Atlas was not coasting, it was driving. The cosmos had revealed a traveller that moved with the precision of an engine, the silence of a shadow, and the efficiency of a design no one on Earth yet understood. In the darkness beyond Mars, a faint, steady glow trailed behind it. Too weak to be exhaust, too structured to be coincidence. Some called it reflection, others something else entirely. Whatever it was, one truth united every observer who watched the telemetry scroll across their screens that night. There was power inside 3i Atlas, and it was not meant to be found. Motion always reveals design. Whether it's the arc of a planet or the drift of a satellite, trajectory speaks the language of geometry, an unbroken record of force, balance, and intent. And when astronomers began plotting the precise path of 3i Atlas through the inner solar system, they realized they weren't just looking at movement, they were looking at control. The first clue came from the vector residuals, tiny differences between where the object should have been under pure gravitational influence and where it actually appeared in space. Normally these deviations are random, the result of outgassing, solar tides, or instrument error. But the residuals for 3i Atlas weren't random at all. They followed a pattern, oscillating smoothly in both radial and tangential components, perfectly synchronized with its changing solar angle. That correlation startled researchers at the Jet Propulsion Laboratory. When they plotted the data over time, the graph produced an elegant waveform, a series of small but rhythmic adjustments, like a pilot making course corrections along a predetermined route. Each change aligned with a specific shift in solar illumination, suggesting that the object was actively reorienting itself to maintain an optimal reflective geometry. In other words, 3i Atlas wasn't drifting, it was steering. To understand how, scientists examined how light pressure interacts with shape. The force of radiation is weak, but it depends critically on the surface's orientation relative to the incoming photons. A concave structure can focus momentum in one direction. A convex one can spread it. If the object were flat, it would accelerate directly away from the sun. But Atlas's acceleration contained a sideways component, a constant lateral drift that couldn't be explained by symmetry. The only logical conclusion was that its surface was angled, adjusting incrementally as it moved. This is where the concept of geometry of control was born, the idea that the shape of the object itself acted as its guidance system. Imagine a sailboat without a rudder, steering only by shifting its sail to catch the wind. The data suggested 3i Atlas was doing something similar, using light as wind and shape as steering. At the European Space Operations Centre, engineers simulated a reflective structure with variable curvature, a shallow dish capable of rotating microscopically to change thrust direction. The results were astonishing. With minor adjustments in angle, the model reproduced both the magnitude and direction of 3i Atlas's acceleration, matching each subtle deviation logged by stereo and punch. The best-fitting configuration was not a sphere or cylinder, but a thin, asymmetric arc, perhaps tens or hundreds of meters wide. Aerodynamic in principle, photodynamic in execution. The more precisely they modelled it, the more it resembled an apparatus. A controlled, functional geometry, not a lump of debris. Even the light curve supported the theory. Its brightness pulsed faintly every 40 minutes, corresponding exactly to the oscillations seen in the polarization data. That meant the object's surface was rotating, not tumbling randomly, but executing consistent half-turns as if to redistribute sunlight evenly across its surface. The precision of those movements hinted at stability beyond anything nature achieves through chance. Skeptics proposed that thermal torques, uneven heating across the surface, could create these spins naturally. But thermal torques fluctuate chaotically, while 3i Atlas's movements were measured, graceful, predictable. The geometry responded to solar input like a feedback loop. The more energy it received, the smoother its corrections became. It was as though the object understood its environment, not consciously but mechanically, as a machine tuned to its star. By late November, researchers began describing the phenomenon as adaptive orientation, not propulsion, not guidance, something subtler, a structure built to respond. No control system visible, no moving parts observed, yet every vector suggested deliberate stability. In an internal note circulated between ESA and NASA, one line stood out: shape as intelligence. It captured the unsettling beauty of what they were seeing, an object whose design alone encoded its ability to navigate space. 3i Atlas had no thrusters, no visible power source, no command signal. But through geometry, through the simple act of light meeting shape, it commanded its own fate. It moved not like a rock obeying the laws of physics, but like a craft designed to use them. And as it glided silently beyond Mars's orbit, one realization began to take hold among those who studied its path. Perhaps control does not always require intention. Perhaps, somewhere between physics and design, the universe has already built the perfect navigator, and we have just watched it leave. When the data finally reached the highest levels of NASA and the European Space Agency, the reaction was not excitement, it was caution. The discovery of a truly interstellar object accelerating without a visible cause should have been the scientific story of the decade. Instead, it became an administrative one. What happened next revealed as much about human nature as it did about 3i Atlas itself. The first internal briefing took place on November 11, 2025, in a small teleconference linking Pasadena, Darmstadt and Cambridge. The meeting began with an unassuming slide deck titled Post-Perihelion Kinematics of 3I Atlas. But within minutes, the conversation shifted from analysis to containment. The graphs on screen showed clean, undeniable acceleration vectors, 135 km per day squared radially, 60 transversely, persistent and smooth. One attendee later recalled that the call grew silent enough to hear the hum of the microphones. NASA's public affairs liaison was the first to speak. "We can't lead with the anomaly." That sentence set the tone for everything that followed. A draft statement was written immediately. Neutral language, heavy on context, light on conclusions. It would describe 3I Atlas as an active interstellar comet exhibiting non-gravitational motion consistent with solar influences. Nothing more, nothing less. At the European Space Operations Centre, a similar memo circulated that same week, stamped internal, not for distribution. It warned staff not to speculate in interviews or social media posts. Some took it as routine prudence, others felt the weight of suppression. Within days, public updates about 3I Atlas slowed to a trickle. The official NASA tracker that once refreshed hourly began updating every few days. The gap did not go unnoticed. Behind the scenes, however, activity intensified. Agencies formed a joint verification task group, quietly bringing together experts from the Jet Propulsion Laboratory, ESA's Comet Dynamics Division, and several independent observatories. Their mission was to confirm, or disprove, the acceleration data before it reached the press. The group's private server became a crossroads of raw telemetry, photometry, and simulations. Passwords changed daily. Access was restricted to fewer than 20 people worldwide. Meanwhile, internal disagreements began to surface. Some scientists argued that transparency was essential, even if the explanation was incomplete. "If we hide uncertainty," one astronomer wrote in a leaked email, "we surrender the public's trust." Others feared a repeat of 2017 when speculation over Oumuamua's strange motions spiraled into media chaos. "We'll lose control of the narrative," replied a senior communications officer, "and once the public hears artificial, there's no pulling that word back." In the weeks that followed, the debate became less about physics and more about language. Drafts of the official bulletin were edited line by line. Phrases like anomalous reflection were replaced with photometric deviation. Possible internal structure became complex albedo behavior. Each revision stripped the discovery of emotion, turning it into something sterile, almost bureaucratic. The caution extended to imagery, high-resolution data from the high-rise. Camera aboard the Mars Reconnaissance Orbiter, rumoured to have captured 3I Atlas in early October, was withheld pending further calibration. Rumours spread that the image showed a geometry too symmetrical to be natural. NASA neither confirmed nor denied it. The silence fueled speculation online, which only reinforced the agency's instinct to tighten control. By late November, a coordinated communication plan was in place. All press inquiries about 3I Atlas were routed through a single spokesperson. Scientists working on the project signed temporary non-disclosure agreements. Even routine telescope schedules were classified to prevent journalists from guessing when the next observation window would occur. Internally, though, the tone had shifted from skepticism to unease. The data had been checked, rechecked, and cross-validated. It was real. The acceleration existed. The spectral anomalies were genuine. The polarization curves, the cooling, the geometric stability, all confirmed independently. The longer the silence lasted, the heavier it felt. "If it's natural," one researcher whispered during a private call, "why does it feel like we're protecting it?" By December, NASA and ESA agreed to release a minimal technical update. The statement landed like a whisper. 3I Atlas continues to exhibit non-gravitational effects under investigation. No context, no press conference, no elaboration. Outside those walls, the scientific world waited. Students, journalists, amateurs refreshing data portals that no longer refreshed. Inside, the institutions built to study the unknown were now guarding it, afraid of what the truth might become once spoken aloud. It wasn't conspiracy. It was something subtler, a reflex to protect the order of things, to shield the public from uncertainty, and perhaps to shield the scientists themselves from the realization that for the first time, they might be studying something not just unexplainable, but aware of its own motion. Heat is the most honest signal in the universe. Every process, chemical, nuclear, or mechanical, leaves it behind. Even the faintest energy exchange, from dust colliding in space to photons striking a satellite, radiates warmth. Nothing moves, burns, or shines without generating heat. That is why the temperature readings from 3I Atlas unsettled so many scientists. The object was accelerating, brightening, and interacting with sunlight, yet it remained cold. The data came from the James Webb Space Telescope in early November 2025. Its mid-infrared instrument, MIRI, was pointed at the region of space where 3I Atlas had just crossed its perihelion. Webb was expected to record a thermal spike, the signature surge that occurs when solar radiation begins vaporizing surface material. Instead, the instrument saw almost nothing. The spectral flux was flat, no rise in infrared intensity, no sign of warming. At first, engineers suspected an observational glitch. Webb's detectors are so sensitive that a single misalignment or calibration error can erase signal, but after multiple re-observations and comparisons with control targets, the results stood firm. The surface temperature of 3I Atlas was roughly 200 Kelvin, about minus 70 degrees Celsius, astonishingly low for an object that had just skimmed within 1.3 astronomical units of the Sun. For context, even icy comets warm dramatically during perihelion, often exceeding 300 Kelvin as volatile ices sublimate. Those reactions are violent, generating both heat and light. Yet here was an interstellar visitor glowing intensely in the visible spectrum, electric blue and radiant, while emitting almost no heat at all. The paradox was impossible to ignore. Physicists at the Jet Propulsion Laboratory began referring to it as the cold burn. The term captured the contradiction perfectly. Something was producing visible energy without thermal consequence. When they ran energy balance equations, they found that less than 1% of the absorbed sunlight was re-emitted as heat. The rest vanished, converted, reflected, or stored by an unknown mechanism. One explanation was extreme albedo, the measure of how much light a surface reflects. If 3I Atlas were nearly mirror-like, it could reflect sunlight without absorbing it, staying cool even as it blazed visually. But the numbers didn't fit. To reflect that efficiently, its surface would need to approach a perfect albedo, nearly 100%, which no natural material possesses. Even polished ice or metallic regolith can't achieve that. Another idea involved phase change shielding, the theory that trapped volatiles might absorb heat through sublimation without releasing much radiation. But spectra from SOHO and STEREO detected almost no water vapour, carbon dioxide or dust, ruling that out as well. The coma was non-existent, the tail invisible. Whatever was keeping the object cold wasn't chemical. Then came a more unsettling interpretation. Several researchers proposed that 3I Atlas might possess an active thermal regulation system, a surface engineered to reject heat deliberately. The polarization data already hinted at microstructured materials capable of manipulating light. If those same structures could scatter infrared wavelengths back into space, they could maintain internal stability regardless of proximity to the Sun. Essentially, the object would cool itself in real time. Such control would require extraordinary precision, nanoscopic lattices tuned to absorb certain frequencies while rejecting others. In laboratories on Earth, metamaterials with partial versions of this ability already exist, prototypes designed to stay cool under intense illumination. But nothing natural can maintain that degree of selectivity over an entire celestial body. As the analysis continued, a strange secondary pattern emerged. While 3I Atlas emitted almost no infrared radiation, it did produce faint rhythmic fluctuations in the ultraviolet band, subtle pulses repeating every 40 minutes, synchronized with its rotation. The coincidence was too neat. Some suggested these pulses represented internal energy redistribution, perhaps electromagnetic cycles balancing absorbed sunlight and re-emitting it in higher frequencies. Others called it noise, but the timing matched the optical modulation seen in its brightness. By December, scientists were forced to state the obvious. The absence of heat was not an absence of energy. Something was managing that energy differently, converting or redirecting it in a way no natural process could. The conclusion was as unnerving as it was elegant. The object that reflected light like a mirror, accelerated without thrust and stayed cold in the heart of the solar furnace, was no passive traveller. It was a system, one that understood heat not as a byproduct, but as a variable to control, and as it drifted away, still glowing faint blue against the black, it left behind a question no instrument could yet answer. How does something that burns so bright stay colder than space itself? By mid-December 2025, 3I Atlas had cleared the orbit of Mars. The last coronal mass ejection that brushed its path had long faded, and the solar wind around it thinned into the quiet vacuum of interplanetary space. Most comets fade quickly after this point. Their brightness collapses, their motion slows, and their debris tails dissolve into invisibility. But 3I Atlas didn't fade. It steadied. Its light stabilized into a sharp, unwavering point, and its acceleration, impossibly, continued. Astronomers at the European Space Operations Centre began calling this phase the Deep Space Drift. The name was misleading. Drift implies passivity, the slow surrender of motion to inertia. What 3I Atlas was doing looked more like navigation. Telemetry from stereo, still caught fragments of reflected sunlight off its surface, enough to measure precise changes in its speed. Instead of decelerating under solar gravity, it maintained a constant outward velocity, increasing by tiny increments each day. The acceleration curve flattened into a perfect line, consistent, mathematical, deliberate. The sun's pull weakened, but the push did not. When scientists ran long-range trajectory simulations, the results were sobering. The object was no longer following a purely hyperbolic escape path. Instead, its course was curving slightly north of the ecliptic, as if under controlled redirection. Even a deviation of a few degrees at that distance required energy far beyond any known natural process. The model suggested a calculated vector, a chosen exit lane from the solar system. The first question was simple: how? At that range, sunlight was too weak to sustain radiation pressure strong enough to explain the continued acceleration. The energy drop-off with distance is exponential. Yet Atlas behaved as though it was still near perihelion, receiving the same force it had weeks earlier. The thrust hadn't diminished. It was constant, like a spacecraft running on an invisible, endless engine. Engineers at NASA's Jet Propulsion Laboratory re-examined every potential source of error. Parallax distortion, sensor drift, orbital interference, all ruled out. The object was moving precisely as measured. To explain it, they proposed a possibility that made the room fall silent. 3I Atlas might be using the solar wind itself as fuel. If its structure was thin enough and conductive enough, it could in theory behave like a photonic sail coupled with a plasma deflector, redirecting charged particles the way a magnetic field guides ions. Such a system could generate continuous thrust even as solar intensity dropped, a form of magnetosailing once imagined in advanced propulsion studies. The physics was sound, the scale was not. For something that size to maintain such control without disintegration was beyond current engineering. Yet, again, the data aligned perfectly. As Atlas passed the 2 astronomical unit mark, ground observatories struggled to maintain visual lock. It was dimming slightly, but not naturally. The spectral profile stayed blue, its polarization unchanged. It was as if the object was preserving its internal state, refusing to shed material or heat. One observer described it as a mirror receding into the void, still aware of its reflection. In late December, a faint radio echo appeared in background noise from the Deep Space Network. It wasn't a signal in the ordinary sense, just a narrow spike of energy exactly at the frequency band corresponding to Atlas's plasma environment. The spike pulsed once every 40 minutes, the same rhythm that had haunted the optical and polarization data for weeks. Engineers labeled it instrumental interference. The timing, however, matched too neatly to ignore. Meanwhile, orbital predictions began to diverge. In every simulation, Atlas's path bent slightly toward a point far above the plane of the solar system, toward the direction of the constellation Cygnus, the same region Oumuamua had once seemed to aim for before fading from detection. The coincidence stirred unease across observatories. Cygnus, home to one of the densest starfields in the Milky Way, had suddenly become the destination for 2 interstellar mysteries. By the end of December, the object was almost beyond reach of most instruments. The final images showed a glimmering speck framed against the faint light of the galactic plane. No coma, no debris, no fading trail, only the steady electric blue point that had defied heat, gravity, and probability. Scientists began drafting the final report. Its language was dry, almost evasive. The object exhibits persistent non-gravitational acceleration consistent with continuous force application, source undetermined. Yet everyone who had watched the numbers scroll across their screens that night felt something else, not conclusion, but continuation. Because deep down, each of them understood what the equations were describing. Through-eye Atlas wasn't drifting away from the sun, it was leaving, on purpose. Patterns are the universe's handwriting. When a single anomaly appears, it can be dismissed as error. But when it appears twice, or 3 times, it becomes history repeating itself. And by the winter of 2025, astronomers were beginning to see that Three-Eye Atlas was not the first object to misbehave inside our solar system. It was simply the first to make the pattern impossible to ignore. The story began years earlier, with the arrival of Oumuamua in 2017, the first known interstellar visitor. At the time, it seemed like an isolated curiosity, a cigar-shaped rock from another star, tumbling end over end as it passed between Mercury and Mars. But as the data matured, one number refused to fade. The small yet measurable acceleration that pushed Oumuamua away from the sun without any visible exhaust or outgassing. Astronomers argued for months. Some blamed dust jets, others radiation pressure. But the debate ended without resolution. The anomaly was noted, then quietly shelved. 2 years later, Borisov arrived. Unlike Oumuamua, it behaved perfectly. A classic comet, venting gas and dust as expected. Its trajectory followed the physics beautifully. The relief was palpable. Scientists hoped it proved that Oumuamua had been an outlier. The solar system, they thought, was back to normal. But in 2020, unconfirmed data from a smaller, fast-moving body, nicknamed Kinios 2014-0108, reignited the argument. The object had exploded over the Pacific in 2014, long before the interstellar debate began, yet its velocity at entry matched interstellar speeds. The US Department of Defense quietly confirmed the numbers years later. The fragments recovered were metallic, unusually magnetic, and rich in isotopes inconsistent with solar composition. Again, something from outside. Again, something that did not fit. Now, with Three-Eye Atlas, the trend was undeniable. 3 objects from beyond our solar system, 3 visitors, each bending the rules of motion in their own way. One accelerated silently, one shattered with exotic metals, and one glowed blue and cold while steering itself through space. Different phenomena, same defiance. At the Harvard-Smithsonian Center for Astrophysics, researchers began compiling these cases under a single framework, the interstellar object sequence. They searched for overlaps in brightness, polarization, and trajectory orientation. What they found startled them. All 3 objects, Oumuamua, Kinios 2014-0108, and Three-Eye Atlas, entered from nearly the same galactic longitude, a corridor of sky aligned with the outer arm of Cygnus. Statistically, that alignment was absurd. The galaxy is vast and interstellar debris should arrive, randomly. Yet here were 3 paths converging within a narrow 10-degree band. When the data was plotted in 3 dimensions, the pattern became even more haunting. The projected exit vectors, the directions each object left the solar system, also aligned, as if following a shared trajectory through the heliosphere. It looked less like random arrival and more like a route. The possibility that they shared a point of origin electrified the community. Some suggested a disrupted planetary system beyond the local bubble, perhaps an ancient stellar nursery ejecting debris in a common direction. Others whispered of intentionality, a chain of probes, each designed differently, each built to study different regimes of a solar system, one to observe, one to test entry, one to respond. To keep the discussion scientific, researchers reframed the hypothesis as the Cygnus stream model, a neutral term describing a hypothetical current of interstellar material moving coherently through our galactic neighborhood. But beneath the technical language, unease grew. If the objects truly shared origin and timing, why were they so different in structure and behavior? Rocks don't evolve in sequence, machines do. At a private symposium in December 2025, one slide showed all 3 trajectories converging on a single outbound vector, extending into interstellar space. In red letters beneath it were 3 words: "Pattern implies intent." The room went silent. Officially, the report that followed was cautious. It spoke of a statistically notable directional correlation among interstellar bodies of non-solar origin. Unofficially, it marked a turning point. What had once been dismissed as coincidence now looked like choreography. For the first time, astronomers began to speak less about discovery and more about sequence, a chain of arrivals hinting at purpose, as if each object were part of a system moving through the galaxy, probing one star after another, recording, adjusting, leaving. And as 3i Atlas faded into the distance, heading toward the same region of Cygnus that Oumuamua once crossed, one quiet thought began echoing through observatories and conference rooms alike. What if we were never observing one anomaly at a time? What if we've been watching a pattern unfold, step by step, for years? By the end of December 2025, 3i Atlas had vanished from most telescopes, but its implications lingered in every laboratory, agency and observatory that had tracked it. For the first time in modern astronomy, science had reached a boundary that wasn't technological or theoretical. It was moral. The object had raised a question so fundamental that no formula could answer it. What do we owe to something that might not be just an object? When the first internal discussions began, they were framed as protocol, not philosophy. Should further attempts be made to contact it? Should high-powered radar pings be sent to measure its surface? Could the Deep Space Network aim a signal strong enough to bounce off its reflective skin? The questions were practical, until someone asked the one that stopped the conversation cold. What if it's listening? That moment divided the scientific community. Half the room argued that 3i Atlas was likely natural, a phenomenon that simply appeared engineered because of incomplete understanding. You don't assign consciousness to a storm, one astronomer said. You study it. But the others, shaken by months of unexplainable data, the constant acceleration, the geometric precision, the absence of heat, weren't so sure. What if studying it without consent crossed an ethical line humanity had never considered before? At the European Space Operations Centre, ethicists were brought into meetings for the first time in the agency's history of comet research. Their guidance was cautious but profound. They compared the situation to early encounters between explorers and isolated ecosystems on Earth, moments when curiosity unintentionally caused harm. You cannot treat a potential intelligence as an inert sample, one advisor said. Observation is participation. The dilemma deepened when someone proposed sending an active probe to intercept the object, a fast-response craft powered by ion propulsion, capable of reaching its projected path within a few years. The idea was bold, the technology barely feasible, yet the debate it sparked was less about engineering and more about morality. Was it right to pursue something that might have come here by choice, now clearly departing? Would intercepting it be an act of discovery or intrusion? In Cambridge, a small working group of scientists and philosophers drafted what they called the Declaration on Extrastellar Neutrality. It outlined a simple principle. If an interstellar object exhibits active behavior inconsistent with natural motion, humanity should observe but not interfere. Non-contact until comprehension, the declaration read. The document never became official policy, but it circulated quietly through agencies, a kind of whispered code of conduct for a situation too new to legislate. Meanwhile, others rejected restraint. We send radio waves across the galaxy every day, argued one physicist. We're already speaking. Pretending we're silent is hypocrisy. To them, 3i Atlas represented an obligation, not a risk. The first tangible evidence that the universe contained something more than lifeless mechanics. Refusing to engage, they said, was an abdication of human curiosity itself. But beneath all the debate was a quieter fear. That contact, even unintentional, might change us more than it changed the object. If 3i Atlas was artificial, it represented a civilization, or what remained of one, so far ahead of us that we couldn't distinguish its machinery from nature. To look upon that and claim understanding might be the deepest arrogance of all. As 3i Atlas drifted beyond detection range, the ethical question became not whether to reach out but whether to interpret. Every assumption about its purpose, its motion, even its silence said more about humanity than about it. We were projecting meaning onto something we did not, and perhaps could not, comprehend. In the end, the consensus was uneasy. NASA and ESA jointly agreed to cease active observation once the object's signal fell below threshold. It wasn't framed as ethics, just resource reallocation. But everyone involved knew what it truly meant. The decision to stop looking was the first act of respect humanity had ever shown to something beyond itself. And so, in the record books, the final note was simple: object lost to detection. But in quiet corridors and private emails, another truth was written between the lines. Sometimes, the most human thing we can do when faced with the unknown is to let it go. By late November 2025, the entire scientific world had entered a strange kind of holding pattern, a silent countdown toward a date that no one had officially marked, yet everyone understood. December wasn't just the end of a calendar year, it was when 3i Atlas would reach the edge of reliable observation, crossing the final telemetry threshold where light faded into noise. After that, it would be gone. The weeks leading up to that moment felt less like research and more like vigil. At the European Space Operations Centre, the final observation schedule was set for December 15th. After that, the angle of the Sun would make tracking nearly impossible, and 3i Atlas would vanish behind the glare of the heliosphere. In emails and private notes, the mission teams began calling it the disappearance window. The phrasing felt uncomfortably human, as though they were preparing to lose someone, not something. Every day leading up to mid-December, observatories across the globe took turns pointing their instruments toward the faint blue point that had defied every law of motion and thermodynamics. The data, however, refused to change. The object's brightness curve stayed constant. Its acceleration remained linear. Its spectrum still leaned toward the electric blue edge that no comet or asteroid had ever displayed. It was as if 3i Atlas was locked in a state of equilibrium, a perfect balance between propulsion and silence. At NASA's Jet Propulsion Laboratory, engineers continued running predictive simulations, trying to determine where it would go once it cleared the Sun's influence. All models converged on the same result. The outbound vector intersected a corridor of space leading toward the constellation Cygnus, the same region associated with Oumuamua's trajectory years before. That alignment, now a pattern, reignited unease among those who remembered the earlier debates. Too many coincidences, too much symmetry. Meetings that had once been crowded with analysts and press liaisons grew, smaller. The conversation shifted from discovery to meaning. If it's leaving, one researcher said during a call, then maybe it was never meant to stay. Others nodded, saying nothing. By that point, few believed they were studying a comet anymore. They were documenting an exit. The countdown reached its final 10 days and the instruments began to struggle. Stereo. A picked up intermittent reflections, weaker with each pass. The object's blue glow flickered slightly, though not in decay, more like a signal dimming as it slipped beneath a horizon. The Deep Space Network detected faint radio echoes, perfectly timed with the same 40-minute rhythm that had haunted the light curves for weeks. Once again, the frequency matched the plasma field readings from late October. It was almost as if the object was broadcasting a heartbeat, one last pulse before silence. On December the 12th, a final joint briefing was held between NASA, ESA, and several university observatories. The tone was somber, restrained, reverent. No new hypotheses were offered. Instead, the meeting focused on archiving. Every byte of data, radar, optical, polarization, spectral, was copied 3 times and stored in separate vaults. One scientist suggested releasing the full dataset publicly. The proposal was quietly denied. "We don't even understand what we're giving away," a senior advisor replied. Then came December 15th. At Yo 312 UTC, the last confirmed optical trace of 3i Atlas was logged by the Subaru telescope in Hawaii. It appeared as a single point of blue light, unwavering, its magnitude faint but stable. 30 minutes later it was gone, no fade out, no gradual decline, just a clean cut-off, as if a switch had been flipped somewhere beyond the edge of the solar system. The silence that followed was almost physical. Scientists watched their screens in disbelief, waiting for another blip, another pulse. None came. Within hours, data collection officially ended. The reports that followed used neutral phrasing, object lost to background interference. But everyone knew what that really meant. The countdown was over. In the days that followed, observatories around the world performed one last act of ritual, turning their telescopes toward the coordinates where 3i Atlas had last been seen. Nothing, only stars, only the faint afterimage of blue in the mind's eye. Some called it an ending, others called it a departure. But in the quiet that settled across mission rooms and labs that December, one truth took root among those who had watched it leave. The universe had just closed a door, and no one knew if it would ever open again.